Now let's take some time to look at where did that linear mass distribution come from. So, center of mass, part 2. So let's look at our little triangular shape that we had before. You'll notice it's a triangle, height L, and we want to get how much mass I get in this little sliver dm. Well, how am I going to do that? Well, first things first, I want to call attention to the fact that this is an isosceles triangle, and we'll call this vertex angle theta. Now, since we said this is a very slim triangle, theta is small, and we will make use of the small angle approximation, where the sine of theta is approximately equal to theta itself, just to simplify our algebra a little bit here. So let's start by looking at the area of the whole triangle. Well, the area of the whole triangle is, like an area of a triangle, going to be 1/2 base times height. The height of the triangle being pretty obvious, L. Now, this is an isosceles triangle, so I can drop a vertical and get half of the base is L sine half of theta. So my base is twice L sine theta by 2. So 1/2 base times height looks like this. Now, if I replace sine of theta by theta over 2, we get a whole lot of canceling, and we find that the area is 1/2 L squared theta. And so the mass density, the area mass density, sigma, is going to be m divided by this area, so 2m divided by L squared theta. So we've got an area mass density. How do we get a linear mass density? Well, let's look at the triangle up to the little dx segment, this little black segment, and including it. So the area in this blue up to that point is going to be 1/2 x squared theta. We'll call x the distance to our little dx. And if we include the little dx, well, we'll get x plus dx as our length. And so the area of the blue plus that little black shaded area is going to be 1/2 x plus dx quantity squared times theta. Well, what's the area of the black? Well, we take a difference. Now that does mean we have to expand this square in taking the difference. So when we do that, we get the following. And we're going to make an approximation. Well, dx is an infinitesimal. We have an implied limit here. We have the implied limit as dx goes to 0. Dx squared goes to 0 far faster than dx, so we'll ignore that term. And so our approximation actually becomes x dx times theta as the area of this small black slice. So what's our mass? Well, the differential mass is going to simply be the area of the black divided by total area times the mass, or sigma times the area of the black, if you like. Either expression is, of course, exactly the same, because sigma is mass over the total area. And so what we will see is the following, and simplifies pretty quickly. So we notice that dm is 2m divided by L squared theta times x dx theta. Thetas cancel. So we get 2mx over L squared dx. And if we remember, dm is lambda dx. So we have discovered lambda. 2mx over L squared, just as we had used in the first problem.